In this lesson, we're going to be going over the TCP IP model. So here is the TCP IP model. Now, the TCP IP model looks kind of stripped down by comparison to the OSI model, and there are reasons for that. And we'll talk a little bit more about that in a second. So in 1989, RFC 1122 was published. RFC 1122 is a request for comment that specifies an architectural model for communications between internet hosts. Now, it's important to note here that this is some 9 years, give or take, after the adoption of the OSI model by the ISO. So we've got the OSI model in place, but TCP IP has become the standard protocol across what was slowly becoming what we now think of as the internet today. So we've got this TCP IP networking stack or networking suite of protocols, and in 1989 they published this architectural model. When we talk about OSI, we talk about layer 1, layer 2, layer 3, up to layer 7. When we're talking about the TCP IP model, the layers were only referred to by name. There was no numbering that was actually referenced. So the IETF manages the architecture and documentation, and it's been updated several times since the original publication with RFC 1122. So we've got the network access layer. And if you're kind of thinking about the OSI model in your head, we're going to flip back here to the TCP IP model, and we've got the network access layer at the bottom. And what that really is the data link layer and the physical layer of the OSI model. So it handles the physical connection. It handles error correction and control on the physical medium. It specifies how messages are translated onto the physical medium, whether it's electrical signals or optical, and what that looks like and what the framing is going to look like. What we've really got here is the physical layer and the data link layer from the OSI models really wrapped up in this network access layer. And the TCP IP model is a little bit more compact in that regard. Rather than separating the two out because they're so closely tied together, they just created the network access layer. Now we've got the internet layer. This is the same as the network layer in the OSI model. IP and ICMP were intended for this layer. This is really where the robustness principle is really in play here. You'll hear the robustness principle referred to from time to time, whether they call it the robustness principle or not. It says, be liberal in what you accept and conservative in what you send. And that really came from a guy by the name of John Postel, who was really critical in the early days of getting the ARPANET and the NSFNet and the different networks that created the internet. He was really critical in helping do a lot of organizational work and managing the RFCs and doing a lot of other work around IP addresses and that sort of thing. So John Postel always said, be liberal in what you accept and conservative in what you send. And that really applies here at the internet layer. It keeps systems up and it keeps everybody working together and talking together. So the internet layer specifies processing rules, and that helps ensure that datagrams end up where they're supposed to. Although different datagrams may actually require reassembly at this layer because they could end up being fragmented. Now we have a transport layer, same as the OSI model, where we had the transport layer. TCP and UDP are transport layer protocols, and they handle end-to-end delivery. UDP doesn't actually care whether datagrams arrive or not. As a result, you'll hear UDP referred to as an unreliable protocol, and TCP handles connection-oriented communication. By that, I mean TCP guarantees delivery, and it also makes sure that there's somebody on the other end to receive it. So there are reasons for having these two different protocols. Sometimes we just want to throw messages out onto the wire, and we don't really care whether they get there or even what sequence they go in. If you think about doing a phone call over the internet, using Skype as an example, when I am talking to you, I want the messages going from me to you to get there as quickly as possible. If some messages end up getting lost along the way, I don't really care so much because your ear's probably going to correct for it. And if it doesn't, then I don't really want it coming out of sequence because then it's going to sound like garbage to your ear. I really just want to send it what gets there, and it gets played. If it doesn't get there, I'm not going to bother trying to resend it. TCP handles the bulk of communications across the internet because most of the time, like web communication or file transfers or things like that, I really do care whether packets get there and what order they get there in, and I want to make sure that they get reassembled correctly. So we've got a couple of different use cases, and both UDP and TCP have their appropriate places in terms of network communications. Finally, we have the application layer. All application functionality is here: session management, presentation, APIs. These are all at the application layer. Again, we go back to the model here, and you'll see there are 4 layers. So the network access layer actually takes up the lower 2 layers of the OSI model. The application layer takes the top 3 layers of the OSI model. It's not like they took the functionality and just discarded it with the TCP IP model. What they said was, we don't really feel that this needs to be broken out into its own individual layer. And as I mentioned with the OSI model, there's sometimes confusion about exactly where different protocols sit, particularly with the session layer. So in the TCP model, they just made it a lot more simple, and it's really just 4 layers. So we've got the network access layer, the internet layer, the transport layer, and the application layer. So TCP IP is a 4-layer model. We've got network access, internet, transport, and application. And that's the basics of the TCP IP model.